All right, in this video, we are going to look at how other conjugated pi systems, in addition to benzene rings, can also be aromatic. Okay, what do we know about benzene here? Okay, well, if you look at the conjugation, it's complete all the way around the ring. There are no interruptions in the conjugation. There are no sp3 carbons getting in the way of the conjugated pi systems here. And there's also 6 pi electrons in complete cyclic conjugation. We're going to see that many of the aromatic systems that we look at are going to have this property, 6 pi electrons in complete cyclic conjugation. All right, let's look at other molecules that are completely conjugated. All right, so the first one we're going to look at here is cyclobutadiene. It has 4 pi electrons in complete cyclic conjugation. But one of the things that so we're going to look also at 1,3,5-hexatriene, which has 6 pi electrons in conjugation, but the conjugation is not complete all the way around the ring. Right here, there's an interruption in the conjugation from this one sp3 carbon right here. Okay, so because of that sp3 carbon there, the conjugation, we say, is not complete. All right, but it does have 6 pi electrons in conjugation. And the last one we're going to look at is this one called 1,3,5,7 cyclooctadiene, which has 8 pi electrons in complete cyclic conjugation. All right, so the question is, do these compounds, they have some things in common with benzene, but do they show this unusual stability that we associate with the benzene ring system? And the fact is, they don't. All right, cyclobutadiene is not a stable molecule at all. It was not synthesized for the first time until in the 1960s, and it was noted that it was unstable at above liquid nitrogen temperature, and it had to be isolated in the presence of a liquid or solid argon matrix, and only then could it actually be observed spectroscopically. It's actually a very unstable molecule. Okay, and its instability, or it's what it does at very low temperatures, is it does this Diels-Alder reaction with itself, okay, to produce that tricyclic system there. I'll just show that Diels-Alder reaction right here. All right, so we're reacting like that. All right, and that set of arrows gives us this compound right here. All right, 1,3,5-hexatriene is a stable compound, but it doesn't show the unusual stability properties of benzene. What we find here is that it's no different from any other conjugated diene system, okay, and it reacts just like an alkene. So reaction with bromine makes the dibromo, or it makes an addition product like you see here, and we have issues with 1,2 versus 1,4 versus, I guess in this case, 1,6 addition. But what we see here is that there's no special stability associated with this, with these 6 pi electrons right here. All right, cyclooctadiene, we also see that it reacts just like a normal alkene. It's stable at room temperature, but its reactions are very similar to what we would expect for a typical alkene or diene system. In this case, actually, you only get 1,2 addition products. We'll talk about that in a second. All right, so this unusual stability seems to require that we have 6 pi electrons in complete cyclic conjugation. All right, so this gets us to Hckels Rule. It means a compound is going to show aromatic stabilization, and Hckels expanded the definition beyond 6 electrons. But here's his theory right here, that we're going to show aromatic stabilization if there are 4n plus 2, where n is any integer, pi electrons in complete cyclic conjugation. What 4n plus 2 means is that the number of electrons in conjugation is divisible by 2, but not divisible by 4. So Hckels numbers are 2, 6, 10. Okay? And this is due to molecular orbital theory. All right. When you have this situation here, we have a situation where the HOMO is far beneath the non-bonding line, and the pi electron MO energies of completely conjugated cyclic molecules. We can sort of look at them by Frost diagrams here. And here's what we do to construct a Frost diagram to arrive at the molecular orbital description of a completely conjugated cyclic molecule. All right, we're going to draw the circle, place a horizontal line halfway. This is our energy of non-bonding. Okay, we're going to inscribe the perfect polygon in the circle, vortex down. There's benzene. We're going to place the lines representing the molecular orbitals where there are points on the polygon. Okay, so there are our 6 pi molecular orbitals of benzene, and then we're going to erase the polygon. All right, so there's the benzene MOs. All right, so if we have this molecule here, recognize that there's no bond right here. Okay, so this is 135 hexatriene. The orbitals just stack up in a linear fashion, one on top of each other. Okay. All right, when we do this Frost diagram for cyclobutadiene, what we find here is that our HOMO orbitals are actually on the non-bonding line. Look how in cyclobutadiene they're up here on the non-bonding line, whereas benzene, they're way below it, even farther below where the HOMO is in 135 hexatriene. Okay? All right, so what we're going to see here, we look at the energy of the HOMO. Okay, is that the HOMO energy is lowest in the benzene ring system. It's way below the non-bonding line. Okay, it's pretty close to, a little closer to it here in the system where it's not cyclically conjugated, and it's right at the non-bonding line in cyclobutadiene. All right, we're going to look at this last one here, cycloheptatrienocation. And it's kind of interesting here. When you do the Frost diagram here, you also see a similar stabilization where the HOMO orbitals are well below the non-bonding line. Okay? All right, so we're going to say that aromaticity is due to this stabilization of the HOMO compared to non-cyclic analogs. And we're going to call these systems here aromatic. They're going to show this unusual stabilization. All right, in this last case, what we see here is a carbocation. Remember how we said that carbocations are unstable and they exist only as reactive intermediates? Well, it turns out this one you can actually isolate. Okay. All right, you can actually, there's some companies that actually sell that. So that's a stable carbocation. All right, so this seems to validate Hckels' theory. All right, so we have complete conjugation all the way around the ring here because the carbocation, remember, is in a p orbital. Okay, let me just draw that here. All right, so this is what we're drawing, remember. All right, so this one is our empty p orbital. All the others are pi bonds. All right, we have a pi bond there, pi bond there. But what you see here is that we actually have 6 pi electrons in complete cyclic conjugation. All right, so that is aromatic. In systems where there are 4n pi electrons in conjugation, okay, this should be cyclization, cyclic conjugation. All right. What we see is that the system is actually less stable than you would anticipate it to be. All right, and we call these systems anti-aromatic. They're destabilized relative to the non-cyclic compound. Okay, so what we see here in essence is that the HOMO orbitals in the anti-aromatic system are higher than in the non-cyclic system, and the HOMO orbitals are lower than the non-cyclically conjugated system when the system is aromatic. Okay, so we're going to call that system anti-aromatic. And we're just going to call this system non-aromatic. All right, so these are our three classifications we're going to give to conjugated pi systems: non-aromatic, aromatic, and anti-aromatic. All right. After Hckels Rule came out, people started building molecules to see if they could spot aromaticity in higher conjugated polyene or higher conjugated cyclic polyene systems. All right, so cyclooctadiene, which has 10 pi electrons, and the isomer here, which also has 10 pi electrons but has 2 trans double bonds. These were prepared, and it was found that these actually are not aromatic. They have a difficult time achieving planarity. Here, there's a severe steric interaction between those two hydrogens that make it very difficult for this molecule to achieve planarity. All right, this reaction here, cyclooctadiene, remember, we didn't see any unusual instability associated with that. We said it was reacting like a simple alkene, and this is also due to non-planarity as well. So cyclooctadiene adopts this tub-shaped molecule, and the double bonds don't overlap. It's essentially as if they're not conjugated, no net conjugation. So what we see here is not a destabilization, but it's reacting just like a normal alkene. So we would say this is a non-aromatic compound instead of an anti-aromatic compound. All right, so someone made this compound, 18-annuline, and in this case, the hydrogens that are inside are so far apart from each other that they don't interfere. Okay, and this one adopts the planarity nicely. And this one does show aromatic stabilization. It has a hard time reacting with the reagents that alkenes react with. And when we look at chapter 13, we're going to see there's spectral properties associated with aromatic ring systems as well that are common to 18-annuline as well as to benzene. Okay, well, we looked at cycloheptatrienyl we saw that we could also have aromatic stabilization in a charged compound. Okay, all right, so if we look at ionic compounds, we can also find systems that are aromatic. Okay, so here is cyclopentadienyl anion. This is also aromatic because the lone pair can contribute to the conjugation. All right, recall when we looked at the VSEPR rules how a carbanion would prefer to be sp3, but what we see here is that if you hybridize the carbanion sp2, it's less stable by about 20 kilojoules per mole, but remember that when you go from non-aromatic to aromatic, that's a stabilization of greater than 130. So what happens here is that this carbon here will adopt the sp2 geometry because now you have a p orbital, and the p orbital can participate in the conjugation. So here's the cyclopentadienyl anion drawn completely as a delocalized system. Here is the same drawing with the individual electrons and lone pairs. And what we see here is that when we count the number of electrons in complete conjugation, there's 2 here, 3, 4, 5, 6. There's 6 pi electrons in complete cyclic conjugation. No problems with planarity. This is an aromatic system. Okay. An empty p orbital can also contribute to the conjugation. Remember that a carbocation has sp2 geometry. The p orbital, even though it has no electrons in it, is still overlapping with the pi bonds. Recall the resonance stabilization of allylic carbocations in the previous chapter. Okay? All right, so here is cycloheptatrienocation. I guess I drew it a few slides ago, but here we have the delocalized system, and here what you see here is there's complete cyclic conjugation all the way around the ring because we have a p orbital at every carbon, and when we count the number of electrons, 1, 2, 3, 4, 5, 6, there's 6 pi electrons. This positively charged compound is in fact an aromatic compound. All right, let's look at some other aromatic ions. This is cyclopropenylcation. This is 2 pi electrons, and this is an aromatic system. Even though it looks like there's an awful lot of angle strain in this molecule, it's actually a relatively stable carbocation. You can't isolate it, but it has a long enough lifetime that you can observe it. Okay? This is the cyclooctatetraenyl dication. It has 6 pi electrons in conjugation. Normally, we can't even think about isolating dicationic species, but this one, again, it's not stable enough to isolate, but it's stable enough to observe. All right, this is the dianion, and remember that in the anion, we actually have p orbital lone pairs. Okay, so we have a couple of electrons there, a couple of electrons there. When you count up the number of electrons that you have in complete cyclic conjugation, 2, 4, 6, 8, 10 pi electrons, this ends up being an aromatic compound. You can generate this compound by treating cyclooctatetraene with 2 moles of lithium or sodium metal. Okay, all right. And you'll generate the dianion. Okay, so what we see here is that even though cyclooctatetraene itself was adopting a tub shape, these molecules here are planar, and this is because when planar, they are aromatic. Okay. All right. This certain hydrocarbons actually show some unusual features. This is the molecule azulene. Probably no surprise here that it's blue based on its name, and it has 10 pi electrons in complete cyclic conjugation. If you go around the ring, 2, 4, 6, 8, 10, even though they're in different rings, they are completely cyclically conjugated and planar. Azulene is kind of an interesting compound, not only because it's blue, but because it is actually very polar. Okay? And it's polar because we can write this resonance structure where there's 6 pi electrons in the 5-membered ring through the cyclopentadienyl anion resonance form, and there's 6 pi electrons in the 7-membered ring through the cycloheptatrienol cation resonance form. All right, this is the molecule chalcocene. It's also very polar, and this is because we can draw this resonance structure here where the 3-membered ring is aromatic because it has 2 pi electrons, and the 5-membered ring rather is aromatic because it has 6 pi electrons. And this is a very unusually polar compound for a hydrocarbon. All right. So let's look at a problem here. We're going to try to predict which solvolysis reaction is going to occur at the fastest rate and try to explain that. And remember that the solvolysis reactions are in fact SN1 reactions, so we are primarily interested in carbocation stability. Okay, so what we would want to think about is the carbocation intermediate that's involved in these. Okay, all right, here, pretty good carbocation intermediate. It's positive charge flanked by 2 alkene groups, like you see here. We know that it's stabilized by resonance because it's a doubly allylic carbocation, but because it's not cyclic, it's not aromatic. We see that some of the other choices below actually are cyclic, so probably one of those is going to be aromatic. This one, if we look at the carbocation, is actually not a particularly good one because it's anti-aromatic. You see that it has 4 pi electrons. And this solvolysis reaction actually occurs very slowly. The next one involves the cycloheptatrienol carbocation, a carbocation that we've looked at before, and we know all about how stable this one is. And this one now proceeds through an aromatic carbocation. So far, C looks like our fastest solvolysis reaction. And finally, D, had we not gone to this chapter yet, we would have picked D probably because it involves the tertiary carbocation. But now we know that aromatic is better than tertiary, and aromatic is also better than conjugated, so or better than allylic. So we're going to predict that C is going to be the fastest solvolysis because the carbocation intermediate is highly stabilized due to being an aromatic structure and thus relatively easily formed. The rate determining step, remember, in SN1 reactions is carbocation formation, and this carbocation here is uniquely aromatic amongst all of the choices here. If we wanted to rank these, we would probably say that reaction C is faster than reaction A, which is faster than reaction D, which is faster than reaction B. Okay? All right, so I think this is where this video ends, and we're going to look in the next video, in the last video for the aromaticity chapter, on how we can use oxygen, nitrogen, and other non-carbon heteroatoms to also construct aromatic systems.